it's time. Any questions from homework? Aaron?
5.1. Number 1.
Number 1. Number 1. Consider the area under this from here to here. And what's the approximation area under the curve? Okay. Oh. Area under on 0 pi over 3 4 using 4 right rectangles. Okay, we will first do this and then left rectangles will be similar. What we will do is we will take we divide it into 4 parts. Okay, that's gonna be pi over 3 divided by 4, which is pi over 12. So this is pi over 12, 2 pi over 12, and 3 pi over 12. That will be the 4 points you're looking for. Now, if you're looking for 4 right triangles, this will be the first, this will be the second, this will be the third, and this will be the fourth. So R4 equals pi over 12 times cosine pi over 12 plus pi over 12 times cosine 2 pi over 12, which is pi over 6, plus pi over 12 times cosine pi over 4 plus pi over 12 times cosine pi over 3. Is everything good so far? Okay, that will be the setup. I think everything here you will be able to do it except for this one. And for this one, you need to use the half angle formula. So if you find it's too much, you can always use the calculator. But I would just do this. Cosine pi over 6. Okay. I don't think there is any necessity to simplify anything unless you want to. Okay, so this will be the answer. Okay, if you find this is confusing, you can also use a calculator to do this. Now for 4 left rectangles, you basically take this, and this to be the 4 left. So you start from 0, you end at 3 pi over 12. Okay, that's how we do this. Nick?
Can you go over 5.2 number 15 and 16, please?
Okay. 15. Oh, 16. Okay, let's go over 16 first. Okay, suppose we already know from 5 to 12.5. 5 to 7.5. 7. And from 10 to 12.5 is 6. We're looking for the following. Number 1, from 7.5 to 10. Of course, we want to use the property. Okay. Let's see. Can you see this one is actually from 7.5 all the way to 12.5 minus? Hold on, what am I doing? Oh yeah, that's right. So we want to play with the ending point in order to get 7.5 to 10. That's my goal. I know from here to here, so I know from 7.5 to 12.5. Okay, yeah. All the way from 7.5 to 12.5 minus from 10 to 12.5, you should have from 7.5 to 10. That's good. And this, we already know it's 6. From 7.5 to 12.5 is from 5 to here. Minus from 5, 7.5 to here. No. From 5 to here. And then we have a minus 6 from the previous one. So this is 10. This is 7. Together, it's negative 3. That's for number 1. Okay. Now for number 2. Okay. You already know how to find from 7.5 to 10. From 10 to 7.5 is just going to be negative. So by linear property, you can take it from here to here. Okay. Second, you realize this one is nothing but if you switch this. You just need to put a negative sign here. Finally, from the previous question, you know this is 3. So together, it's going to be negative 10 times negative 3. This is going to be 30. Now from 10 to 70.5, 7. Now use the properties we had in class. 7 means it's a constant. If it's a constant, what you're having here is nothing but a rectangle. So this is going to be 7 times the ending minus the starting. So I would say this will be the answer for the second one. Okay, where is my, okay. Yeah, my Chrome started updating, so it closed all my tabs before. Nick 5.2. Number 16. Okay, so it's gonna be 37.5. What is 2.5? Oh, sorry, 47. Okay. That would be number 16. So basically you play with the ending points and make sure that you have the ending points you want. Okay. Now for 15. You were trying to find this. So what you want to do is you want to follow whatever WebWorks wants. Okay, that's fine. Step 1, find delta x. And delta x is nothing but 7 minus 3 divided by n. So that will be the width of the rectangle, which is 4 over n. Number 2, you want xk star. Moreover, you want the right point formula. Okay. Now, what you have here is you have an interval. You start from 3, you end at 7. You want the right end formula. So this will be the first, this will be the second, and keep going. So if you're looking for the ith interval, the ith interval should be a left point and a right point. So it should be starting from 3. Okay. Go for 4 over n for each step, and for I steps. Okay, for example, the first interval, you have 3 plus 4 over n. The second interval, you have 3 plus 4 over n times 2. The third interval, you have the 4 over n times 3. So eventually, the ith interval will be 4 over n times I, if you're using the right formula. So 3 plus 4 I divided by n. Okay, they use k, so 4k divided by n. All right. Now you want the rectangle. The rectangle is going to be f xi star times delta x, which is just this. Delta x, you already find it is 4 over n. F, 3 plus 4 over n times k. But now you know your f is nothing but 2x. So together, do we want to simplify a little bit? That's going to be 8 over n times 3 plus 4k over n. Okay. Number 4, sum k from 1 to n f xi star xk. I keep doing this. Okay. Delta x is going to be sum I from 1 to n, 8 over n times 3 plus 4k over n. Okay, now we need to actually simplify this. What is it? Well, you have two terms. So let's write it down. 24 over n plus 32k over n squared. Okay. The first term is going to be 24 over n plus 24 over n plus 24 over n. Keep going for n terms. So the first term is going to be 24 over n for n times is going to be 24. The second, of course, we don't really care about 32, but we care about 1 over n squared plus 2 over n squared plus 3 over n squared plus n over n squared, which is 32 times n squared, and the one on the top, we have done it in class. That's going to be n times n plus 1 over n. So together, this is going to be 16 n plus 1 over n squared. This formula is in class. We counted the chocolate and everything. Okay, so together, Rn should be 24 plus sum. Oh, this is already done. Sum plus 16. N times n plus 1 divided by n squared. Okay, finally, for the last case, number 5. You let n goes to infinity. Okay. The first one is still 24. The second one, you can use the leading terms. It's going to be 16. So together it's 40. Sounds good? All right. So that's how much trouble we have to go over in order to do a simple integral. Okay, Riemann sum. Now remember, you just want to do this, right? With the fundamental theorem of calculus, do you remember? That's going to be the antiderivative. What's the antiderivative of 2x? X squared, right? Put a 7, put a 3, finish. Number 1, you got the right answer. Number 2, it's way faster. Okay, so that's the beauty of why we need 5.3. Without 5.3, now you will be doing this all the time. Okay, which is something we try to avoid for sure. All right, Adam.
Could you go over 5.1, problem 10?
Problem 10.
Yep.
Okay. Definition, the area of this one. Okay, use the above definition to determine which of the following expression represent. All right. Okay. Number 10. Okay, you want integral from 0 to 1 x cubed dx. I will do it really quick. Dot x is 1 minus 0 over n, which is 1 over n. Okay, and then you need a sum I from 1 to n, 1 over n times f x on I star, which is sum I from 1 to n, 1 over n. Here, it really depends on, do you take the left point? Do you take the right point? If you take the left point, it's going to be I minus 1 over n to the cube for left. If you are going to take the right formula, it's going to be I over n to the cube. And you can see the difference is just like, are you taking the previous one or are you taking the next one? From here, you can see number A is going to be the final answer. Okay. The rest is try to figure out how to do the Rn. So Rn is sum okay, which is 1 over n times from here you can see, okay, number 1, it's 1 over n to the 4th. Number 2, you need to know how to sum all the cubes together all the way up to n. Luckily, Weber could give it to you. Okay, so this formula here is given by Weber. Sounds good. Once you have that, now you just need to take the limit. N goes to infinity. Rn. What's the limit of this Rn? Well, we just need the leading term. The leading term on the top, on the bottom is going to be n to the 4. The leading term the leading term on the bottom is going to be n to the 4. The leading term on the top is going to be n squared times n plus 1 squared, and you need the leading term, so that's going to be n to the 4th. So together it's 1/4. Okay, again, with all the trouble. Now, if you just take a look, do you know the antiderivative? Of course. Which is 1/4. Again, this is way better than Riemann sum. Okay. All right, Anton?
Yeah, so my first question was whether you were planning on posting the notes for Thursday and Friday from last week.
Oh yeah, I forgot to do it. Yeah, I'm
Okay.
gonna do it after today's class, with today's lecture.
And then my other question was that for these kind of problems, like on the exam, are you gonna like ask us to use one or the other, or is it our option whether to use fundamental theory of calc or Riemann sum?
So if I write down this without saying anything, you have the choice to use either. And I think if you choose to use Riemann sum, I will be really sad. Okay. So don't use Riemann sum unless I ask you to. And in the exam, I will not ask you to take the limit of the Riemann sum, because that involves, you can see, 4 steps. If you make every single mistake in any steps, you will screw up the whole thing, right? So what I would probably do in the exam will more be like use 3 right triangles. Right rectangles using right point formula. I will probably give you some examples like that. Not something like you need to actually do the n and then take the limit. Okay, it's just too much in the exam.
Sounds good.
Yeah. Other questions? Questions from the homework? Okay. I'm glad actually you guys did some of the homework, so you totally see the advantage of the fundamental theorem of calculus, right? With that thing, now you don't have to worry about Riemann sum at all. Otherwise, this one takes forever. Okay, 5.3 is done. That's one single formula. And it's a great formula named after Leibniz and Isaac Newton. They went in like, I don't know, 44 years, 54 years of controversy. And finally, they went to the court, and still you don't know who invented it. So basically, we put both names there. But it's a fantastic formula. With that formula, we now know how to do every single problem about finding the area under the curve. So that's nice. We also talk about how to do this. That is, if you have something like, that's the accumulation function, right? But then we say, well, what if I change this x to be cosine x? Okay, I'm still trying to do the area. I'm asking you the changing rate of the area, but somehow the right ending point is actually moving like crazy. And moreover, what if I change both of them to be moving? We kind of talk about how to do it using the chain rule last time. Okay, that will be the second thing we need to worry about for 5.3. Other than that, it's done. Now we went to 5.4. It's going to be a quick section. We already know all the big ideas. It's just like, okay, putting them down, make sure they're formal, well-defined. And finally, how to say, we want to define the net change theorem. So let's talk about the indefinite integral of number 1. I always write this, find the antiderivative of fx. Okay. This is pretty dumb. Every time you see something, you just write down a sentence, and you're doing it for so many times, you must define a notation for that. For example, I don't want to say find the derivative. I just write down f prime x, and you know what I mean. Right? Similarly, you should define some notations for antiderivative. Should be something simple like fx, worst case anti. And then we just say, hey, this is the agreement. If you see this, you do the antiderivative. It's going to be way better than this sentence here. But we'll wait it until now. And the reason is because now we know more. Not only we know the antiderivative, we also know it's related to integration. Okay? So we better use the same notation with integration so we don't invent two things, basically means the same thing. Okay? So what do you know about integration? Well, I know this. And basically the antiderivative is part of this. Sounds good? The antiderivative is which part? The antiderivative is this part without a and a b. Still okay? That also means if you find antiderivative, you plug in ab, you actually have the definite integral. So how about we just take this notation without ab, and we just say this means finding the antiderivative. What's good? Number one, it's not too bad of a notation. It's long. It's longer than f prime. But number two, in this way, you kind of connect the antiderivative and the integration together. Okay, so that's why this is probably the best notation we can think of. Of course, we call this definite integral. We definitely call this one the indefinite integral. The idea is quite simple. With AB, it's going to be a area, it's going to be a number. Without AB, it's going to be the antiderivative. So that's the notation we defined for antiderivative. Then next time, if I want you to find some antiderivative, I don't have to write down the sentence anymore. I just say, hey, please go ahead and try to find this. Okay, do you know how to do it? We have nothing better but to split everything. Then you realize, okay, this is 4.9. Finally, when you finish, do a plus C. Sounds good? Just a notation. Question, what is this? Number one, you can compute it. You're going to compute the derivative first, which is going to be a product where you're going to have two terms. And can you imagine the two terms are not easy. Now you want to take the integration. And for now, the only thing we know how to take the integration is just the formula. Some simple ones, right? So probably we don't want to go ahead and solve it. Just by looking at it, what do you think the answer will be? You have a function. What do you do first? You take the derivative. After that, what do you do? You take the antiderivative. What will happen if you take the function, you take the derivative, and then you take the antiderivative? You don't change a thing, right? Okay, so from now, you know by definition, it's this plus a C. You also know then, if you take this, and then you take the derivative, it's probably going to be the same thing. Right? Do you have a plus C here? Not really. Okay, why? Because plus C only shows when you have integration. If you take the integration, you have a plus C, then you take the derivative, the plus C is gone because the derivative of the C is 0. Sounds good? From here, you can see a very simple thing, which is kind of tricky. That is derivative and taking the antiderivative inverse operation. You have done a lot of inverse operations before, right? Plus is the information of the minus, right? Times is the inverse of dividing. Still okay? If you have a number, you times 3, then you divide by 3, you got the same number. If you got a number, you divide by 3, and then you times 3, you got the same number. Good so far? So this is actually the idea of inverse function. That means if you do f first, f inverse second, or if you do f inverse first, f second, you still have the same thing. From the beginning, derivative and antiderivative should be inverse, right? That's what the word anti means. But now if you think about it, can you see that? There's one small thing you need to be careful of. Can you see if you take the derivative and then you take the antiderivative, you will have a plus c. But if you take the antiderivative and then you take the derivative, you will not have the plus c. So when you do these two things, the order of you doing it actually matters. It depends on, do you do the derivative first or do you do the antiderivative first? You have different answer. Okay, from here, you can see actually they are not inverse to each other, even though it's very likely they're inverse to each other. But if you switch the order, they don't give you the same thing. Okay. That's roughly what we have. Okay. Number 2. Number 2 has nothing to say. It's just this formula, which we talked about last time. Next time when you see definite integral, you just do the integral first, which will give you a function. After that, you plug in b and a. Sounds good? Okay, quick example. Integration of x minus 2 from 1 to 3. Now, we know the notation. Find the antiderivative first. Keep everything, but put 3 and 1 here. Okay, the rest is, why do I do this to myself? Minus 4. Ho, 0. Nice. Okay, so that's how we do the thing. So basically, you just do the antiderivative first. The rest is plug in the derivative, plug in the ending point. From here, you can see the indefinite plus the ending point. Probably don't do plus. Yeah, just the plus. Will give you the definite integral. So basically, when you say indefinite, you basically means I don't know the ending point. Okay, when you say definite, that means I do know the ending point. So either way, I'm trying to find the area. It's just that for one case, I don't have the interval. So there's nothing to talk about area. So how about I give you the general area, which is the antiderivative. Okay. Third thing, the net change theorem. What it says is AB f prime x dx equals fa minus fb. Oh, sorry, fb minus fa. At first, this looks like nonsense, right? This is just like redundant with what we had before. You take the integration of something and it equals the antiderivative b minus a. But now if we're talking about net change theorem, try to read this in words this time. The accumulation of the changing rate is the change. Let's use a more significant word. Is the total change of fx on AB. Okay, let's say you go to the casino. I don't know, at 0, and then you leave the casino at 10. So you play 10 hours in the casino. Okay. Now from 0 to 1, how much money did you win? You win $40. Between 1 to 2, how much money did you win? Actually lose $20. Okay. The next hour, you plus 30. The next hour, you minus 10, whatever. Eventually, you have a lot of changes. You have 10 changes actually within the 10 intervals. Good so far? So now what I'm going to ask you is, how much did you win or lose in the past 10 hours? What do you do? You basically just sum them together, right? My total change from 0 to 10 is my change from 0 to 1 plus my change from 1 to 2 plus my change from 2 to 3, 3 to 4, 4 to 5, and so on. So my total change equals the sum of individual changes. Good so far? Now let's go say you go inside. This time you don't play the thing. I don't count the whole thing every single hour. I count it every half an hour. So from 0 to 10, before you have 10 intervals, now you have 20 intervals, right? You have 20 changes, right? So what's the total change? You just sum the 20 changes together. Okay. Now what if I counted every single minute? How many minutes are there in 10 hours? There are 600 minutes. So you're going to have 600 small intervals. And for each interval, you have a change. What's the total change? That's the sum of the 600 different individual changes. It's going to be very small. Within 1 minute, probably you just don't lose anything. Or maybe lose like $0.2 or things like that. Still okay? Do you see where this is going? I'm pushing it to the limit. What if I'm just randomly assessing? Actually, I'm assessing every single moment of how much you lose or how much you actually gain. Number 1, how many intervals are there? Infinitely many. Okay? How much do you gain or lose within one small little tiny interval with 0 length? You lose nothing, you gain nothing. Because there's no time. Still okay? But somehow, I want to sum all these changes together. So what do you think the total change will be? That will be the sum of individual changes. But now something changed. Number 1, it's not going to be the individual change anymore. It's going to be the individual changing rate. Number 2, it's not going to be the sum anymore, because when you say sum, you need to have finite many intervals to sum together. But now you have infinitely many. You should take the integral instead. Okay? So your total change is the sum of the individual change. But when you push things to the limit, when you have a continuous index of what you're earning at any moment, you just want to accumulate all your changing rate together. That will be your total change. That's what the theorem means. Sounds good? All right, so let's see some examples. Number 1, if you accumulate all your velocity together, what do you get? Your velocity is the changing rate of what? Distance, right? So if you accumulate all your velocity together, you will know the change of distance within the past 2 hours. Okay. What if you accumulate all the accelerations together? That's going to be the change of velocity. Kind of make sense here? Okay, think about it. How can you do that? Well, let's say you're pushing a cart. Let's say you don't have a speed meter, so you don't know how fast the whole thing is traveling. Still okay? But what you do have is actually you have a pressure sensor at your hand, so you know how hard you push the thing. Okay, and you also know how heavy that thing is. So if you use how hard you push that thing divided by the mass, you got the acceleration at any single time, right? Okay, so just by the feeling from your hand, if you record it at every single moment and you take the integration, you will know how much velocity actually added to the whole cart. Even though you didn't directly measure the velocity, you only measured the changing rate of the velocity. But as long as you take the integration, okay, with the feelings in your hand, you will be able to know I made the whole thing traveled 20 miles hours faster than before. Still okay? It's very, very useful. For example, what if you accumulate oil leakage? So let's say you have an oil tank and it's leaking. It's leaking at, I don't know, 20 liters per second, ideally. But of course, sometimes it's 19, sometimes it's 17, sometimes it's 26. Okay, so at different moment, you can put a sensor there and try to measure. You will have a curve telling you sometimes it's leaking really slow, sometimes it's leaking really fast. You have a curve. Now, what's the total leakage? What's the total leakage during the past, I don't know, 7 hours? That's going to be the total. If you integrate, which is basically accumulating all the changing rate during the past time. So total leakage during AB. Sounds good? That's basically what the net change theorem gives you, which is very important. There are some simple facts you know before in physics. If I put a VT curve here, do you remember what your teacher told you? If you have a VT curve and somehow you want to find the displacement, you simply just take the area. Right? Okay, now you know where it comes from. Of course, because you are taking the integration. You're accumulating all the velocity together. Of course, that's the area. So the area becomes the distance. If you put how much you gain from the stock every day, how much you make in the stocks every day. Okay, time. Sorry, this should be TV. Okay, this will be the stock profit every single day or every single moment, right? If you actually ask your algorithm to trade it automatically for you, you will have actually for every second, you will know how much you earn and how much you gain because the price is constantly changing. Good so far? What's your total gain? Yes. Okay. Now, if you think about it, actually for the previous case, where we say, well, you win $30, you win $40, you win $50, you simply just plus them together, right? Even for that case, which you don't have anything continuous. I'm just going to take the P. What you're actually doing is actually you are having 30 times 1, and then 40 times 1. Yeah, I mixed the color. I should have red. Oh. So even before, when you try to say the total change is actually nothing but the sum of individual changes. And each individual change actually have a fixed interval and have a fixed height, which is 30, 40 for every single minute or for every single second. Good so far? Even for that case, you were taking the integral. It's just you're taking the integral of some constant function. That's why you can actually say, hey, number 1, number 2, number 3, and number 4. Okay, so I will just draw and give you the idea of what we're talking about. And even if you lose money, okay, you lose money again, you win money again, you lose money again. So you're still doing the area. Now you can see, okay, finding the area is actually same as summing all the bars together. If summing all the bars makes sense, then finding the area makes sense. Okay, or if finding the area makes sense, summing all the bars of course makes sense. All right. Is everything clear on this? That's basically the net change theorem. So it's conceptual. There's nothing to compute here. Just keep in mind one thing. That is from now on, if you just integrate all the changing rate, you will be able to have actually the next level of knowledge. That is the total change. Okay. Finally, the substitution rule. we will go ahead and try to do the integrals, which is a little bit harder than just the formula. We start with example like this. We kind of talked about this before. The answer is sine x squared. Can you see why? Chain rule. You pretend you didn't see this, just handle sine. When you finish, you times 2x. Okay, going forward is pretty easy once you are familiar with the chain rule. Now the difficulty is how do you go backwards? Okay, when you go backwards, now you know what you should look for. Number one, you should look for something. Number two, you should look for the derivative of that thing coming from the chain rule. Sound good? So every time you see a new function, if you want to use this substitution rule, the first thing you should look for is I should see something which is a part of what I'm having. Meanwhile, I see the derivative of that part. Okay, that's number one. Once you know that, what do? You pretend you didn't see x squared. You just say it's just something that I'm going to treat as a variable, right? I don't worry about the derivative of u because your derivative is actually outside. So what I'm going to do is I'm going to actually give you a name. Then what I'm looking at is nothing but this. Which changed to this. Now I can ignore x squared and focus on cosine. And if I focus on cosine, I know it's sine. Because the distraction is gone. Good so far? Okay. But the distraction should be there. But what do you know? You know everything here is nothing but the derivative of u. Okay. So that's by chain rule. Finally, once you get rid of the distraction, you find the final answer, you should put it back because you started with x, you better finish with x. Make sense here? This is the idea of u substitution. We call it u sub. And you have done this a lot of times before. Okay, for example, have you done some problems like this before? It's confusing. You got sine, you got square, you got all these kind of things, right? But the first thing you realize is actually if you let u to be sine x, what I'm having here is nothing but u squared minus u minus 2 equals 0. What does this u do? This u actually get rid of the distraction and let you focus on something simpler. Good so far? But what about the distraction? Once you finish u, you handle the distraction later. But for now, you can put it aside and focus on the macro structure. Similar here. What do? Well, I'm taking a u. Why do you want to take a u? So you don't have to worry about x squared anymore. Let's focus on the macro structure first. Okay? What about the leftover about x squared? When you finish, you just add it back. Okay? So if you accept this idea totally makes sense. It's just this time when you try to replace things, you have to be a little bit careful because you have the derivative involved. Okay, that's the only difference. Okay, let me write it down. U substitution. Okay. Basically, you want to do this. Moreover, you realized, well, I do have a function and its derivative. That's the moment I realized I should really just let u to be gx. Why? Then the function become easier. Let's skip this first. The function become fu. Okay. Second, this part together become my derivative of u. And then I can do the integral in a different variable but the destruction of G is gone. Just like the X squared is gone. Sounds good? All right. Let's try some examples. Do you see a destruction function along with its derivative? Do you see it? Sine cosine, right? Cosine is the derivative of sine. So if I see this as my derivative, then this will be my original. This will be my original thing. So if u equals sine u, then du over dx is cosine x. Oh, u equals to cosine sine x, sorry. Then the whole thing becomes 2u, okay? Cosine x is du over dx, fine, times dx. Dx cancel. Do you know how to do the antiderivative of 2x? That's going to be x squared. What about 2u du? U squared. Okay, of course, when you finish, put it back. Your u is sine x, so technically it's sine x squared plus c. Okay. If you want to verify it, take the derivative. What do? You do sine x first. Okay, that's x squared, right? So you have 2x. Forget about sine x. But then when you finish, just attach the derivative of sine x. That's exactly how I did it here. All right. Sounds good? Can you do it in another way? Well, the cosine is the derivative of sine, right? But sine is also the derivative of cosine, modified by a constant. So actually, I can let u to be this too. Then du over dx is just negative sine x. So the whole thing becomes 2 du over dx with a negative sign times u times dx, and they cancel. This is negative 2 du, a u du. Eh? Oh, yes. 2u. Okay. Very easy to do. That's negative u squared plus c, which is negative cosine squared. Make sense here? Okay. So from here, you can see number one, you want to pick one part to be the u, the other part to be your derivative. That's fine. But if they become derivative of each other, it really doesn't matter which one you pick. You pick sine, you got cosine. You pick cosine, you got sine. They all should work. However, they give you two different answers. They don't look the same. Are they the same? Oh, I didn't realize. Okay, it's 11.5.5, so it's already all for today. Tomorrow, come back and think about it. Are they the same answer? They should be, right? Otherwise, your U sub is not working.